Hi everybody, I'm Joel Weiner at Evanston High School, and the last meeting I attended I think probably had less than 10 people, and so I went out on a limb and I made 20 copies. So there's not enough for everybody, so you might have to share. I'll just quickly write my contact info up here if you're interested in more info. If you don't get the handout. All right, so what I'm going to show you is a variety of things that I've been doing this week and the last week, and so I'm going with the theme of doing what we're doing currently. In my class, it's looking at atomic structure, and what I'd like to do for you is what I like to do for my students, which is to go beyond the basic material. So we learn about, of course, the nucleus, protons, electrons, neutrons, etc., and Bohr's model and all of that sort of stuff. But once we've gotten through that, I like to stretch it, see where we can take it. So I have a few demos to get through that. And the first demo I actually don't have because it requires deuterium oxide, which is very expensive, and I already used it up. I just freeze some deuterium oxide and I drop it in some distilled water. And so it's pure water and it's ice, and it just sinks to the bottom very quickly. And this is done as a demo for the class. I just say the ice is pure water. I have distilled water in a beaker, and I just drop the deuterium oxide in the beaker. It sinks to the bottom. Pure water ice, pure water in here. How could that happen? How could the ice sink when we all know that ice floats? So that's it. That's my whole demo for the class, and I have them. I say, go home if you think you can figure it out. Just type up your answer and send it to me. So of course, the deuterium is slightly heavier. It's the H2 isotope. And so it's slightly heavier than the H2O water, and that's why it's.
Where do you get it?
I have the website where I get it, and if you don't have this, just send me an email, and I'll be happy to send you the website. I mean, it's not terribly expensive, but I use it up. I get a little batch and I use it up. It's very interesting. I have a second question. As I get to my fourth and fifth class, it no longer sinks. And so I asked them, okay, well, all my other classes, it just sank. And now it's starting to not sink. And so I'm telling you, I'm sorry it's not sinking for you, but can you come up with a reason why it's no longer sinking? So it stretches their minds, and anyway.
If you want to save it, you can put it into a barrel pipette, squeeze all the air out of it, and then seal it with a hot
A hot what?
tongs or pliers. And then do the same thing with water.
So seal it in a vacuum, is that what you're saying?
No.
Seal the end of it, heat the end of it, and seal it so it melts shut.
With no air in it.
With no air in it.
And then do the same thing with water.
Okay.
And then when you drop them in, the one with deuterium will sink, but the water one will float because the total density is less than one for the water one because of the barrel pipette, but the other one is still, and then you'll never run out.
And to be able to distinguish them, you put a drop of the dye in, like a blue dye for water.
If you want.
Okay, that's
so you
cool.
can tell the difference between the two.
So I can just buy one batch and I'll be set for the rest of my life. Okay, that's great. Thank you very much. All right, and so when we're doing the Bohr model, I have lab. Probably many of you do this. I have spectrum tubes, and we're looking through spectroscopes to look at the emission spectrum. And so we talk about the interaction of light and matter. And so to take that a step further, I like to. PowerPoint? No, this is. So I like to visit global warming now and then. There's so much chemistry in global warming, and so this is the first time that I can really get some chemistry out of global warming and give them some access to it. So this is, I'm sorry I don't have the citation for this, but I could send it to you if you really want it. So what this is showing is the percent of carbon-13 in CO2 at this bottom graph over the last 1,000 years. The percent of carbon-13 CO2 is quite constant over that 1,000 years until about 1750 at the beginning of the Industrial Revolution. The percent of carbon-13 goes down dramatically. Simultaneously, the percent of CO2 in the atmosphere goes up dramatically. And the reason for that is because plants fix carbon-12 CO2 almost exclusively. And so what this is showing is that so this isn't a demo, but I think this is an unusual illustration that people really don't see very much. And what the discussion what I want them to get out of this is, number one, if plants are only fixing C12 CO2, number one, and plants are the resource for the hydrocarbons that we burn, that we use for our fuels, then what is the source of the increase in carbon dioxide in our atmosphere? Well, it's C12 CO2, as shown by the fact that the C13 CO2 percent is dropping dramatically. And so if the atmospheric CO2 keeps on increasing, by proportion, we're not adding any C13 CO2. And so by proportion, that keeps on decreasing as the C12 goes up. So if plants fix C12 exclusively, and all our fossil fuels come from plants, what does that tell us about the source of the increase in CO2 in the atmosphere? It's human generated. And I think this is an extremely important point to get across to students, that global warming is not just a problem, but it's a problem that we have been part of. We have been instrumental in producing the increase in CO2. And then I talk about, does this graph make sense? Does this?
The other thing the top graph says is that there are people who say, oh, but the atmosphere is so complicated. When you put more CO2 in the air, it's going to be absorbed by the oceans, and plants are going to react better with it. They're going to take it in. And I want you to show me in the top graph where the ocean is absorbing all this extra CO2. Whatever it's doing, we're overwhelming it, if there is any.
Right. Sorry, was that a question or a statement?
No, it's just a statement.
Okay.
It's a statement. It's a puzzle, a problem you can fix.
Yeah, thank you, okay. All right, all right, so to go along with this, I went a little over. So this is, I just grabbed everything I've been doing the last week, couple of weeks. And, all right, so what I do, and is I have two clear plastic bottles, one labeled CO2 and one labeled air. And I have 200 watt incandescent bulbs. Unfortunately, these are now worth a lot of money because you can't buy them anymore, as far as I know. Is that correct? Well, anyway. So what I'm going to do to demonstrate, so after we talk about this, I talk about how the infrared is absorbed by the Earth and re-emitted as, I'm sorry, the UV is absorbed by the Earth and re-emitted as infrared.
Let out the air. Jumping in the bottle for many years.
He's always a wise guy.
Okay, so I think, so what I'm going to do, this is a little awkward without a ring stand, but I can do it, so. We'll just deal with it. Couple of. All right, so while we're waiting for the ring stand.
Did we get the will page? Oh, I got the journal.
So, notice I didn't say now, but.
Wait.